All right, so now this is the last section from chapter 2, and this is cylindrical and spherical coordinates, and we want to convert from cylindrical to rectangular coordinates and back, and then convert from spherical to rectangular coordinates and back. Okay, so let's just start off with something really simple that we did before, and that was looking at the XY plane. And here in the XY plane, I have some point. So I'm going to choose a point, and here is my point. And my point has coordinates X, Y. So here is X, and here is Y. Now, in order for me to get there, I'm going to move over X units, and then I'm going to go up Y units. And I am at the point XY. But there's another way to get there, and that is to swing out a certain angle and then draw a ray from the origin to the point. And when I do that, this angle becomes theta, and the length of this ray is r. And so we've already established that from going from Cartesian coordinates to polar coordinates, we know X is r cosine theta, and Y is r sine theta. And that is how we go from polar to cylindrical, to polar to Cartesian, because this is Cartesian. And these are polar. So that's how we go from polar to Cartesian. We also know we can go Cartesian to polar So that is, if we know X and Y, we know that R squared is X squared plus Y squared. So a lot of times we'll write R is the square root of X squared plus Y squared. And then we know theta is the tangent inverse of Y over X. So given X and Y, we can find R and theta. Okay, so we did this way back before. All right, so for example, if X is equal to the root of 3 over 2, and Y is equal to 1/2, then we know that R squared is X squared plus Y squared. And in this case, that's going to be 3 over 4 plus 1 over 4. So that is 1. So R is 1. And then theta is the tan inverse of 1/2 divided by the root of 3 over 2, which is the tan inverse of 1 over the root of 3. And we plug that into the calculator, or we just know that the angle whose tangent is that is pi over 6. Okay. If R is equal to 2 and theta is equal to pi over 4, then x is equal to 2 times the cosine of pi over 4. That's 2 times the root of 2 over 2. So that'll be the root of 2. And y will be 2 times the sine of pi over 4. And that will be 2 times the root of 2 over 2. And that's the root of 2. So here, I now have found xy to be the root of 2 over 2, root of 2 over 2. And here I found r theta to be 1 pi over 6. Okay, well, the main part of this course is 3 dimensions, so let's get there. Okay, it's going to be easier to do it this way. Okay, so now in 3 dimensions, this is x, this is y, and this is z. So now if I have a point and I go x, and then I go y. So now, oh, I'm sorry, I'm on the wrong axis. That's not x. X is here. So here is x. Let's say I go out this far, x, and then I go, that's why I cannot stand this grid. I cannot use this grid. I have to draw my own. Thank you. Okay. This is x. This is y. And this is z. So now if I have a point in 3 space, I can go out x, I can go over y, and then I can go up z. So here's my point. So this point has coordinates x, y, and z. So now I can think of anything in terms of 3 space, in terms of how far I go in x, how far I go in y, and then how high I go in z. Okay. But now I can also do the same thing I did before. That is, I can take and I can march from the x-axis to an angle. I can then draw a ray from the origin to this point on the XY plane, call that R, call this theta, and then go Z. So now I can go around, and so now this point also is the point R theta Z. So now these are cylindrical coordinates. And the reason why we like cylindrical coordinates is because we can define anything that's in a cylinder easily. So if we have something like this, and then it happens to be round, but it has a height to it. So it's round with height like that. I can talk about how to get there for the radius, and then the angle, and then I can talk about how high I want to get there in Z. So it's nice to be able to use these cylindrical coordinates. So for cylindrical coordinates, this is the rule. X is R cosine theta. Y is R sine theta. And Z is just Z. Similarly, R is still the square root of x squared plus y squared. Theta is still the tan inverse of y over x. And Z still defines the height off the plane. Okay, so the left one is cylindrical to Cartesian. So this one is cylindrical to Cartesian. And the right one is Cartesian to cylindrical. Okay, so cylindrical is very much just polar, except it's off the ground. Okay. Okay. So let's see what we have here. So if you remember, when we had a cylinder, so let's look at a cylinder. Okay, so in Cartesian coordinates, I have x squared plus y squared is equal to a squared. That's the radius of the cylinder. We just talked about that. All right, so this is a cylinder, but it's a circle at a circle of radius a at every height z. So just think of a soda can, okay? So when I draw my cylinder, I have a circle of radius a. It's a pretty bad circle. And then this circle of radius A is duplicated all the way up. Okay, so this is my cylinder. Again, no mention of Z because for every height Z, I get the same circle. Okay, so that's my soda can. It is a cylinder. Okay. So Z is just Z. We don't say anything about Z because we're in 3 dimensions. But in spherical coordinates, I'm sorry, in cylindrical coordinates, well, x squared plus y squared is r squared. So that means we just get r squared is equal to a squared. So that means r is equal to a. So this is the formula for a cylinder in Cartesian coordinates, and this is the formula for a cylinder in cylindrical coordinates. Okay. All right, let's look at a plane. So a plane in cylindrical coordinates, nope, I'm going to do Cartesian first. In Cartesian coordinates, a plane looks like AX plus BY plus CZ is equal to D. Okay, so that's my plane. But in cylindrical coordinates, I'm going to get A times R cosine theta plus B times sine, B times R sine theta is equal to D minus C. D minus C Z. Trying to think how your book wants me to write it. Oh yeah, that's right. So I can just leave it like it was. How about something easy? Say we have the plane x equals 4. Well, that becomes r the cosine of theta is equal to 4. So that becomes r is equal to 4 over the cosine of theta. Okay, so x equals 4 becomes that plane. All right. The plane xy, so the plane y is equal to x. Okay, well, that becomes r cosine theta is equal to r sine theta, but that becomes the tangent of theta is equal to 1. Or that becomes the plane theta is pi over 4. So this second one, if I wanted to draw it, I would come out here, swing out here to where theta is pi over 4. And then I would have a ray. Ooh, that's ugly. I would have a plane going through there. There we go. That's it. There's my plane. I got it now. There's the plane. Because here's theta's pi over 4. So I just have a plane going right straight through there. Okay. How about some of these other things? What else did we have? Let's look at a cone. We had x squared over a squared. Well, this would have to be a circular cone. So I would have x squared plus y squared would equal z squared. So that would be r squared equals z squared. So that would be the cone in cylindrical coordinates. Okay. The circular paraboloid. This is a circular cone. That would be z is equal to x squared plus y squared. So therefore that would become z is equal to r squared in cylindrical coordinates. Okay, do you have any question about any of these?
No, not right now.
Okay, I'm gonna do one more. So I'm gonna do a sphere. So we get x squared plus y squared plus z squared is equal to a squared. So that's a sphere of radius a. So the sphere of radius A. Okay. So that's my sphere of radius A. So therefore, we would take x squared plus y squared, and we would replace that. So we would get r squared plus z squared is equal to a squared. And so that is it in cylindrical coordinates. Okay, so cylindrical coordinates is the easy one. All right, it's fairly easy to be able to draw everything. The one that is more difficult is the spherical coordinates, because Cartesian coordinates is fairly easy. Okay. So now we want to look at what we call spherical coordinates. Okay, so we did cylindrical coordinates. Here it is. So cylindrical coordinates assumes pretty much that we're working on a cylinder, okay, or in a soda can. Spherical coordinates is more in the sense that the points we're looking at are inside of a sphere, okay? So I'm gonna borrow this picture because this picture works for me. Okay, so here we are. This is the world of spherical coordinates. It's very, very, very simple. Why can't I get that to just do exactly where I want it to be? No, you're too high. Just a little bit lower. A little lower. One more. Just don't overshoot right there. Okay. So you see the XY planes, XY axis, XYZ axis. Okay, so now I'm going to do the same thing. Here's my point P. All right, that big red dot. So now I can either go out X over Y and then up Z to get to that point in space. So that's why it is given the value X, Y, Z. I can go out X, I can go over theta. So I can take a ray, find theta, take my ray, go all the way out R, and then go straight up Z. And I'm again at the same point, which is why it is called r theta z. But this is where life gets a little bit more challenging. I could stick where that point is and say, I like the fact that I swing out this far to get to theta. I'm happy with that. Me and that works. So I like swinging out this far to get to theta. But I also like the fact that I can go from the z-axis and swing all the way down to that ray and call that rho. Call that phi. So this is the angle phi. Here's theta. And then I can, instead of going on the ground and then up, I can just go straight to the point from the origin and call that rho. So that is why this is given P can be rho, which is the distance from the origin straight to the point. Theta. Theta is the value that it's still the same angle as if we did the X and the Y Cartesian, or we did the R and the theta cylindrical. Theta is still the same. So right now, X, Y, Z, our definition of R and our definition of theta have not changed. But we're introducing a new angle that I am now calling phi. Okay, and phi is how you take and sweep down to the point from the z-axis. So we can go out theta. So we have rho, theta, and then phi. Okay, any questions about that?
No.
Okay, so now here are our matchups. Our X, we have X, Y, and Z in the Cartesian coordinate system. We have R, theta, and Z in the cylindrical coordinate system. But notice in the spherical coordinate system, the only thing that we actually keep is the theta. We now have something called rho and this new angle phi. And so therefore I need to have a relationship between R and rho. And I need to have a relationship between Z and phi. Because X is still R cosine theta. Okay, so here, X is still R cosine theta. Y is still R sine theta. And Z is still Z. But what happens when I move to here? All right, well, let's go back and look at our picture. And if I look at this and I say, you see the height Z. So this is the height Z. This is a right angle. So I know this length is Z. I know this angle is phi. And I know this is rho, and it is the hypotenuse. It is the hypotenuse for the angle phi. So therefore, if I'm looking at phi and rho is the hypotenuse, then Z yes, Z if I take R, this is the length R, and I take R, which is the opposite, and put it over rho, that is the sine of theta. So I now see, as I'm looking at this angle, that r over rho is the sine of theta. So I need that r over rho is the sine of phi, not theta. Okay. And z over rho is the cosine. Of phi. Okay. So that means x. So what I get from here now is two new equations. That is that r is rho sine phi, and z is rho cosine phi. So these are new equations for me. But now those are the new equations that I need to be able to relate x in terms of rho, theta, and phi, because I can now replace the r inside the x and get x is equal to rho sine phi cosine theta. And now I get y is rho sine phi sine theta. And now I get z is rho cosine phi. Okay. So that's the matchup. So in Cartesian, I have x, y, and z. In cylindrical, I have r, theta, and z. And in spherical, I have rho, theta, and phi. And I can go back between them. Okay. So let's just take for a moment the sphere. So we said the sphere in Cartesian coordinates is x squared plus y squared plus z squared is equal to a squared. And then in cylindrical coordinates, we replaced x squared and y squared with r squared, and we got r squared plus z squared is equal to a squared. Okay. Well, what's r squared? So now let's go down to spherical. Okay. So the spherical, well, r squared is rho sine phi squared. And z is rho cosine phi squared is equal to a squared. So this gives me rho squared times sine of squared of phi plus the cosine squared of phi, and that equals a squared. So this says that rho squared is equal to a squared, so rho is equal to a. So now I have it. For a Cartesian, I get x squared plus y squared plus z squared is a squared. For cylindrical, I get r squared plus z squared is equal to a squared. And for spherical, I just get rho equals a. Nice and easy. Rho is equal to a. Okay. Okay, so I want to identify the volume inside the sphere and out of rho equals B and outside the cylinder rho equals A. So I'm trying to find this empty space left when I push and core this apple. What is the best coordinate system that I should use? Any idea?
No, I'm sorry, I don't know.
Okay, we'll talk about it on Monday, on Tuesday, Monday.
Monday, yes.
Okay, we'll talk about it on Monday, my dear.
See you.
Okay,
Have a good weekend.
you too, sweetie. All right,
Thank you.
bye-bye.